We're going to talk quickly here about one of the other four intro skills, significant numbers. Now, before I get going on this, let's just discuss kind of my general strategy on you learning this and what we're going to do in the class. Number one, it's important to learn significant numbers for the following reasons. When we make measurements, significant figures are a way to communicate to another person how accurate these measurements are. That being said, throughout physics, we're primarily going to focus on other things, so we're not usually going to use significant numbers in our calculations. Why should you know them? If you continue forward into engineering, or specifically some more advanced sciences, you're definitely going to want to know them. So we definitely want to kind of touch base from year to year, similar to what you probably did in chemistry. Let's follow the rules. Number one, all non-zeros are significant. So if you write, let's go here, 92, there are two significant numbers. Next, all zeros between two significant numbers are significant. So if I write 902, 9 and 2 are both significant, so the 0 in the middle is significant, and that has a total of 3. Okay, this kind of presents an opportunity for a strategy that you can just find the first one on the left, the second one on the right, and add everything in between. Next, zeros on the left are never significant. Now, this makes sense when I write a number like 900. Why the heck put a 0 here? There's no thousands, there's nothing in the thousands place, so there's nothing to measure. So yeah, that's not significant. It makes less sense when you do something like 0.009, but it's for the exact same reason. Okay, why isn't this significant? Just like there's not enough in the hundreds place to go to the thousands place, there's not enough here in the thousandth of a decimal to get to the hundredth of the decimal. So there's nothing here, there's nothing to count. So why is it here? Simply as a placeholder to show us that what that size that number is. Next, zeros on the right of the number and right of the decimal are significant. Why? Because why put them otherwise? So if I were to write 0.090 for the previous rule, neither of those zeros are significant, but this one is. So this number up here would only have one significant number. This number here has two. Finally, zeros on the right of the number and left of the decimal may be significant, and there's a bunch of ways to tackle this. The first easy one is if I say 900 versus saying 900 with a decimal. The decimal signifies that I've measured all the places, and so this one would be 1 and this one would be 3. But then you might say, what about if the tens place was measured and not otherwise? There's a few ways to handle this. For starters, if you were dealing with error, you could say 900 plus or minus 10. Okay? This tells us that we have measured the tens place but not the ones place, and therefore we'd have 1, 2, 2 significant figures. But honestly, your easiest bet is just using scientific notation. Because if I write 900 in 3 ways, 9 times 10 to the second, 9.0 times 10 to the second, 9.00 times 10 to the second, 1, 2, and 3 significant figures, but they all say the exact same thing. Scientific notation is nice because you get rid of this rule since there are not going to be zeros on the right of the number unless, of course, they are between two other ones. So, actually, no, I'm sorry, there's just not going to be zeros on the left side of the number. That was stupid. So you're only going to find them on the right side of the number, so you would only write them, boom, if they are significant. Okay, a couple other things to tackle real quickly. Next one is this. Exact numbers are always never limit significant numbers, meaning exact numbers have infinite number of sig figs. For example, like it says here, first example, discrete objects. If there are 25 students, I've counted exactly 25 students. I don't need to worry. That should never limit my calculation. It has an infinite number of decimals behind it. Second, define quantities like conversions are 100%, have all infinite. Even though I don't have any decimals here, it's exactly 1,000 millimeters in 1 meter by definition. And finally, integral numbers that are part of an equation. There's exactly 1/2 of a diameter in a radius, so that too is never going to limit you. Finally, rules on calculations, real quickly here. If you have a multiplication or division, it's pretty simple. Check all of your numbers, how many there are, 4, 6, and 2, calculate completely like normal, and then round to the lowest number of significant figures. So this final answer right here would actually be 75,000, or 7.5 times 10 to the fourth as your final answer. When dealing with addition and subtraction, the rules are a little bit different, but pretty close to. I like to line it up vertically like this because what you're doing is you're going from right to left and finding the place with all significant numbers, or at least where most of them are. So in this particular case, you'll see our significant numbers come out here on this one, and we only got 2 places here, 3 places there, 4 places there, but this is limiting the ones, so that is where it is limited. Now, I'm going to round this. You'll notice this is a complete calculation. I'm going to round to 1,293. Note something interesting here, that I can actually end with more significant figures, in this case 4, than the lowest number. This one had 3. That's entirely possible on addition and subtraction.